All right. Just to catch up with where we left off, all we did yesterday was discuss, the nature and assumptions and such. We looked at the multicollinearity, the KMO, and Bartlett's test of sphericity. We did our basic PCA, that bottom-up PCA that has where we allow as many components as we have variables.
1 second, Austin. There's a quick recommendation that we zoom in on your screen because right now we can see the colors, but we can't really easily see the text.
In here, let me see if does this make it easier? Is that easier?
I think it also needs to be bigger. Is that? Oh, that's better. Is that better for everyone, or do you want it bigger?
Works for me.
Cool. And then we got into our different ways of thinking about the number of components that we would use. And we have, based on the theory, we would expect there to be 3 components because we're looking at the self-esteem, depression, and discrimination scores. Kaiser's criterion, looking at those eigenvalues that are greater than 1, we have 4. Looking at our scree plot, you could make arguments for 4 or 5. Looking at the variance explained, which is there in our summary, where we can look at the cumulative variance explained, and we see that after 5 components is where we have over 50% of that variance explained. And then we're going to look at our parallel analysis. Now for the parallel analysis, that's where that paran library is going to come in. And what we have is the function is called paran from the paran package. And so we'll give it our PCA df, which remember is just the subset of the 19 variables itself. We'll do 100 iterations of it, which is just doing that randomizing or inserting random data, running the PCA, looking at the eigenvalues, etc., doing that 100 times, then looking across all of them. And for now, we're going to go ahead and include an argument all equals true, and we'll explain why after we run it. And so whenever you run that function, this is what your output will look like. And what this is telling you is that when you take these 19 variables across the number of, we have, I guess, 2,164 rows of 19 variables, insert random data into them, and then do a PCA, we look at these adjusted eigenvalues. Now, as a reminder, what we're wanting to do here is compare the eigenvalues that we got, which you could see by squaring that SDev from the PCA. And so, actually, let me run this so this is on bottom. So when we do that, we're comparing these eigenvalues here with the eigenvalues that our parallel analysis gets. And what you're looking for is how many components are there that the actual component has a greater eigenvalue than these randomized simulated ones. Now keep in mind that if you run this over and over and over, you're not going to get the exact same values that you always get. You may have slightly different values just by the nature of it being random. But here we can see that our first eigenvalue, our actual eigenvalue, is 4.7. And down here, the randomized one, we have 4.5. So cool, that one's good. Our next one, we got 1.94. This one's 1.8. So that one's good. Work your way down, and then you can see down here on number 5 where our actual eigenvalue is 0.967, but of our randomized ones, the eigenvalue is 0.892. So that fifth component is where the randomized component has a lower eigenvalue than the actual component.
One quick, just a quick stop. We have a couple of questions about code. So can we first go back to the scree plot code? Linda had a question about if we can see that scree plot code. So it's.
Oh, I guess I need to reload.
Yeah, make sure when you open this all up that you rerun and reload all your libraries first of all.
And so this
And it looks like, Linda, maybe it looks like you have maybe a typo. I think your code looks good. I think there's just a typo. Then I actually didn't get to run the paran because it went by really fast. So can we look at that for a second?
And that's this line right here. And so as Casey also is pointing out here in the chat, that if you notice this adjusted versus unadjusted eigenvalues in the paran code, if you look at this unadjusted eigenvalue column and then look at the actual eigenvalues that we got with squaring that SDEV from the PCA that we did, you'll notice that these values line up with these unadjusted values. And so, in other words, this unadjusted eigenvalue is the actual eigenvalues that you're going to get. And so comparing across, and where are the unadjusted greater than the adjusted?
They're everywhere, right? Each one.
Wait, let me double check that because we got 5, 9, 6, 7,
Until you get to number 10.
That's interesting.
Yeah, something's messed up here.
Yeah, I'm also seeing that now too, because that's strange. What if I do 500 iterations just for grins and giggles here? Bear with me.
Oh, do we know what? We didn't specify the value, how many, what did we have a problem? I'm getting a problem with X. It says error in eigen R, only value. Infinite or missing values in X. I wonder if I loaded the wrong data.
What's the problem?
Well,
this should have yielded 4.
Yeah. And that is really strange.
Oh.
Yeah, because that should have only been 4 as well. Let me check something.
Becca had a good question about no iterations.
Hey Anna, with the former program that we've used, what does that one run for the number of iterations?
Well, you entered in manually. Let me tell you real quick. Hold on a second.
Of course, my computer's trying to lag up.
Okay, we did 100 on that.
Yeah.
So wait, can I ask you a question? Did you actually do this PCA with a random data set? Because these are in fact the obtained eigenvalues, and none of them should have been 4. So it makes me think that maybe the data frame that we're using, we didn't specify a random data frame.
Hang on, I'm pulling up the documentation on this package real quick to double check.
Okay, I'm gonna go up to
You would get this different values if it was random.
yeah, you should.
Well, but that's, I mean, with this function though, like you put in the actual data frame that you used for your PCA.
I had a question. When I put in false for all, it gave me 4. Do you know why that would be?
Yeah.
So,
So that's
It's because it only will show you then the eigenvalues that exceed 1.
that, and so basically the ones that should be retained based on that random thing, kind of if you cross the random data with Kaiser's rule, that if the random eigenvalue is greater than 1, then that many things, and so that's why we put that in there to show initially, but
yeah, I think that we'll have to troubleshoot this one later. I think that it's giving us like the real eigenvalues, and it's doing a slight adjustment for bias, but it is still the real eigenvalues. If we run this as a regular parallel analysis with the other program, it does not, the first eigenvalue is never that high.
it's just so strange since we already ran this and
I know.
it was correct. Yeah, so I'm not sure what's going on there. We'll figure it out and we'll get back to that. Yeah, we're all working without a net here.
Yep.
And Cameron, you asked about number 4. That's what we did yesterday with KMO and Bartlett's test sphericity. But anyway, so we'll get back to the parallel analysis thing, and I'll figure out why this is not behaving the way that it behaved literally up until, you know, we start class. So are we all good to go ahead and move on to number 7? Basically, in this section here, the parallel analysis should be 4 is the answer that we're ultimately going to come to. So based on theory, we have we want to extract 3 components based on Kaiser's criterion, SCREE, or parallel analyses. It'd be 4. And based on the SCREE, you could argue for 5, and looking at the 50% variance explained, we'd be extracting 5 components. So we're going to do different iterations where we do different rotations on 3 components, on 4 components, on 5 components, etc. We're going to work through all of these. We're not going to get very far today as far as like getting through the actual homework, because for these first couple, we're going to really take our time. We're going to write some CSV so that we can open things up in Excel to highlight and sort and like really dig deep on these first couple component analyses. Then when we come back, that's when we'll say, all right, now let's look at 3, let's look at 5, etc., etc. So with that said, going down to number 7, where it's just asking for a table to report the component eigenvalue percent variance explained and cumulative percent variance explained. For this, we already know that to get the eigenvalues, we use that PCA $ SDEV squared. And if you recall, when we ran the initial PCA and I ran this structure to show you that, like, hey, there's a lot of components here, even though if you just run summary PCA, like just that summary command gives you everything that number 7 is asking for except the eigenvalues itself. But this is called the importance table, based from in this package anyway. And so basically all we need to do is bind this importance table with our eigenvalues. So down here we'll have we're going to R bind, we're going to row bind the summary PCA and then $ importance. And then we'll just run just that portion just to make sure that,
I think you have a typo.
All right, so that's working, and then we'll bind that with our eigenvalues via PCA $ SDEV squared. And now when you run that R bind, it has all that information that it's asking for, and this bottom row is not labeled, but those are those eigenvalues that we just attached onto it.
1 second, Austin, please. All right. So in the R-bind table that it outputted, the first row for each, so each component is listed, PCA 1, principal component 2, principal component 3, and so forth. The first row is the standard deviation, which the last row, then the bottom row, is the standard deviation squared, which is variance or eigenvalue. It's the variance explained in the x variables by that component. The second row is the proportion of variance in that component, and the cumulative proportion is overall how much variance in the x values is being explained by the extracted component. So we have everything in one table. Morgan wants to know if there's an easy way to write this to CSV.
With that, let me see. If we take that, and let's just see first what's the structure of that exact thing. So it's a table. Let's see, what if we do that as a data frame? Yeah, so if you make it as a data frame, wrap that in data frame, but then notice that it gives you that this standard deviation, proportion of variance, cumulative proportion, and the blank down here is not listed as it's as the row names. It's not an actual value. So if you just write this as is to a CSV, like your columns are just going to be PC1, PC2, PC3, and it won't have any of those labels. But if you add on the row names to data frame, row names to column, there we go. Then now, like, that row name will actually be a column in the data set, and you'll still have, blank for eigenvalue, but at least then you have the other things labeled, and so then you could just pipe that straight into write_CSV. Give it a title, like whatever. And now over in your working directory, you should have a CSV called whatever. that off so it doesn't try to write it again. All right, any other questions before we go on to the communalities? All right, so here's where we're gonna do another PCA, a separate PCA, and this time we're gonna start with 4 components, and we're gonna be using the Opleman rotation. To do these principal components, well, for the rest of the principal components, we're gonna be using from the PSYC package. The principal is the name of the function. So the first thing that we have to put in is our data frame, PCA DF. We need to tell it the number of the number of components. That's called in factors, even though technically this is a principal component, not a factor analysis. But for the number of factors or principal components, we're looking for 4. Rotate, to tell it what rotation we want Opleman. And then the one important component that actually doesn't even show up in the... So if you look at my screen and where it gives you like RN factors, residuals, rotate, all of like the default arguments, there's another argument that we have to include that isn't listed there, because if you look at the very end where you see the ... what that tells R is that that tells R that there are additional arguments that can be accepted, because what happens whenever you have these functions, that sometimes they work with other functions, that those other functions can also accept different arguments and specifying certain information, that the principal function isn't going to list all the possible arguments for all of the other functions that it uses under the hood. So when you see the ... that just means like, okay, there are other arguments that can be put in, but they aren't specific to the principal package. What we have to do is we have to tell the principal package that we want to do a Kaiser normalization along with this PCA. And so the normalize equals true is the argument that we're going to put in, and I'll let Anna talk more now about why 4 not 5, as well as like this Kaiser normalization, why we're doing Opleman, all that sort of thing. So I'm going to come back here and we're going to name this PCA PCA.OB4, so that we know, because as we're going through all these, we want to be able to know which things we're doing. So this is OB4, means it is the Opleman rotation with 4 components. And so once we run that, we've now done that PCA, and Anna, I'll let you take over and discuss as they work through that.
Okay, so the first thing I want to know is, let's see, Josh asked, is there a specific way we're supposed to report the values for number 7? Can you tell me more? What is your question?
Yes. So in number 7, you're asked to report component eigenpercent variance explained cumulative percent. Is there any certain format, or is this like a table that is normally reported?
Yeah, if you look at your homework, the actual document, there's already a table there. That's all you have to do is fill in those values.
I see. Okay, thank you.
Okay. The next question was from Morgan, and it asked, why are we starting with 4 and not 5? And there's actually a lot of questions that there are multiple sort of probably questions that could be asked here. So why are we extracting 4 components and not 5 or 3 or any of the other options that were available to us? Why are we doing a PCA and not an EFA? And why are we doing a oblique rotation and not an orthogonal rotation? And so the answer is, there's not really necessarily the perfect right way to start. I told you this was an exploratory technique, and so you're allowed to explore. And that means that you can start from this side or start from this side or whatever, but what we're gonna see here is that we're gonna be doing a lot of these. So this just happens to be the first one. Now, the reason that I chose it as PCA with 4 and with an oblament rotation, PCA, because in some ways PCA is a little bit easier to interpret than EFA, since all of the variants of the X variables are thrown into the analysis. So later when we get to EFA, it's, if you've already had PCA experience, it'll be a little easier to understand why EFA, for example, a variable only contributes 20% of its variance to the initial analysis, but in the end has 60% of the 20% explained by the factors. And it's just, it becomes a lot to keep track of, but in some ways PCA is easier because you just throw it all in. So that's why we start with PCA in this instructional set, not because there shouldn't be theory. In fact, there is theory, and probably we want to end up with an EFA. But we'll start with PCA because mathematically it's a little simpler. We started with 4 because across all of the different methods of determining how many components were present in our data, so eigenvalues suggested 4, theory suggested 3, parallel analysis, which we'll fix and figure out why it's giving us the real parallel analysis and not the randomly generated data parallel analysis values. But that one will have given us 4. Then we have let's see, what was the other one? Percent variance gave us 5. So what we really have is a range of 3 or 4 or 5 that we could have started with, because all of those were reasonable given the SCREE, given the percent variance, given the Kaiser rule, given all the methods we have for determining. And I suggested we start with 4 because if we'd been able to do our parallel analysis the way we did it when Austin and I worked on it together before, it is probably the best method. So I figured let's start with like the strongest method we have, but we'll see later in lab, we're gonna go back and do it based on theory. We're gonna go back and do it based on percent variance, and we'll see what happens when we do that. So because parallel analysis said 4, because PCA is mathematically simpler, those are why we're doing those 2. The reason we're doing an oblique rotation is because if you remember, I gave you some guidelines for when is it safe to assume that the dimensions or the factors or components are orthogonal, and when is it really a distortion of reality. And so do you guys remember what was the rule for determining if you were allowed to use an orthogonal rotation or if you were really distorting your data?
I think it was something related to the correlations, right?
Yep, it was the intercomponent or interfactor correlations. We had a particular level of the correlation that if we exceeded, we said we can't pretend like these are orthogonal. Do you guys remember what that was?
In my notes I have, if it's greater than 0.3, we should use an oblique rotation instead of orthogonal.
That's exactly right, Nia. So when we have correlations that exceed 0.3 or about 10% of overlap, right? Because if you square 0.3, you get about 10% shared variance. So if the components or factors are overlapping about 10% or more, then we really can't use orthogonal. The problem is we don't know that until we start by running an oblique rotation, because the oblique rotation output is the only one that gives us the correlations. In an orthogonal rotation, you're forcing correlations to be 0. So there's no need to get output telling you how correlated they are. So if you really want to know, kind of like if you let your dog off a leash and it's like, is my dog going to run away or will it stay close to me? You know, the only way to know that is to actually let it off its leash, which is a kind of a risky thing depending on who your dog is. This is sort of like what we're doing. We're going PCA off leash. We're letting the components do whatever they will, be correlated or uncorrelated, however they want to be. And then we're going to look at the output and decide whether they want to be pretty correlated with each other, or whether it's probably safe to assume that they're pretty independent, and that using an orthogonal rotation, which would be ideal, is fine. So it's a good idea to start every factor analysis with an oblique rotation, so that you can then look at the correlations and then decide whether it's fine to force them to be zero. But if you start by forcing them to be zero, then you can't decide whether you're distorting reality. You have no way of knowing. There's another question here from Casey. What's a communality? And we're about to explain that. I think Austin will probably explain that.
Yeah,
But
well,
I'm happy to explain it as well.
and I was gonna ask. I can pull up that at the SPSS table, and that might help. So
Any questions so far about why we're choosing this analysis as the first analysis?
So if you were to run this analysis in SPSS, one of the things in the output is going to be this communalities table. And it has two columns in it, an initial communalities and the extracted communalities. The reason that I'm showing the SPSS output in particular for this is because in R, in order to get this initial communalities thing, which we won't deal with until we're doing the factor analysis at the end, we have to do it in a very roundabout way. So this initial communalities for now is more of a conceptual thing that you'll need to understand. What the principal function gives you is the extracted, the final communalities. And Anna, I'll let you talk a little bit about what these mean.
Sure. What do you guys notice about here in a PCA, the initial column?
They're all the same. Everybody has 1.0 initially.
Yeah. So what that means is, because this is a PCA, that the variable Discrim 101, the variable SC 101, the variable DEP 101, all of those variables are putting in 100% of their variance into the analysis. So you can immediately tell it's a PCA because every variable is contributing both its unique and its shared or overlapping variance into the PCA. If we're running an EFA, we're going to see the initial column is not that. The initial column is only overlapping or shared variance with the other variables in the analysis. But as we said before, mathematically, PCA throws all the variance in, doesn't take out the uniqueness. That's why the communality in a PCA is always 1 for every variable. Communality literally is like the overlap, or the what the variable, kind of the variance in the variable that is being explained in the analysis. So initially we throw in 100% of the variance in Discrim 101 into the analysis. And in the end, we don't get 100% back because we don't extract 19 components. But in the end, we get back 52.7% of the variance in Discrim 101. How much of the percent of the variance in Discrim 102 are we getting back from this analysis?
.271.
Yeah, or
27%.
27.1%. Yeah, exactly. Josh also wrote that in. So if you look at this table, is it possible to make it a little bit bigger? Awesome. If you look, not quite that big, because I want to see them all. If you look at the, perfect. If you guys look at this table, which variable, after we extracted 4 components, which variable are you going to guess, or which variable does have the most variance explained by the extracted components?
I think depression 104.
We have a vote for DEP 104. What do others think? Yeah. Josh says yes. Elise says yes. Becca, everybody's on, yeah. Exactly. So depression 104 threw in 100% of its variance into the analysis. And then we extracted 4, not 19, but 4 components from the analysis. And DEP 104 has almost 70% of its original variance that can still be explained by these extracted components. So that's a lot, right? That's awesome. Which variable is the one that it's like, this one's really pretty marginal. It doesn't really, the components aren't doing a good job of explaining it. Yeah, we're going to get to the marker issue in a moment, Morgan. But this is our first hint that it will be a marker. So we have a couple of votes here for Discrim 102. Yes, excellent, you guys. You're totally following along perfectly. Discrim 102 threw in 100% of its variance into the analysis, but it's only getting back, right, the amount explained of 27%, which is not shabby. We have seen some as low as like 4 or 5%, but it still suggests to you that maybe this variable is not going to be as cozy with its own components or factors, which we'll look at in a little bit. But that's basically what this table is trying to tell you, is like how much variance got contributed to the initial analysis, and then how much variance explained did it get back from the extracted components. Does that all make sense?
And again, one thing I just want to point out is that the reason that the principal function doesn't have anything for, like, you can't extract this initial thing, because this is important to remember. It's one of the key distinctions between PCA and EFA is that in a PCA, it's always, everything starts with 100% of its variance in there. So anytime you're looking at a PCA, that initial included variance is always going to be 100%, so it's always going to be redundant, which is why we don't get this information from this particular thing. Like I said, later towards the end of this unit, when we get to that factor analysis, we'll be able to compute these initial things to see how much variance is included at the beginning and then how much variance is explained after rotations. But just remember that so when you look at number B on number 8, and it says how much variance is being included, it's always 100% when you're working with a PCA.
So Austin and I debated about whether we needed to show you this table, given that R doesn't provide it for you. But I actually think that because I'm very interested in you guys understanding kind of conceptually what is happening when we're doing these analyses, to me, it felt really important that you actually see this table and that we spend our time in the next couple of labs walking through things kind of slowly. So, you know, we could go fast. We could finish all our output today. We could have probably done half of it last time, but I really, really want you to feel like you're understanding what's going on here. What is it? What's actually happening, both theoretically and at some level mathematically. So we know we're in a PCA. We know that, so that 100% of the variance in the variable is included in the analysis. We got a chance to take a peek here in this SPSS table at how much variance got explained after extraction. We talked about how to extract, or how many to extract. We talked about how it's important to start with an oblique rotation, and there are many, and there's no way. The one thing we're not going to talk about is how do you decide which type of oblique or which type of orthogonal. That's a whole course. But for now, we're just using Obleman. There are a lot of other ones, Promax and others. But the important thing is that oblique rotations let you get the correlations among the components. So then we'll be able to analyze whether it's fair to force it to be orthogonal.
And then also I'll mention, I sent out that email yesterday, but just as a reminder, I made like an 8-minute video that just shows visually like what broadly the idea of rotating data and how that works, and understanding that, oh, it's just multiplying your data by some matrix. And so like each of these different types of rotations basically just has a different matrix that you're multiplying it by. And as far as like which rotation type you're doing, like all the nuances between them, that's just something that you would have to dig into, like looking at all those different types if you were trying to do something. But as Anna has said many times, like that is its own entire course if you're like trying to like really understand the nuanced differences between different types of rotations. It's kind of out of the scope of a survey course. But I did get that up. It's something that helped me understand a little bit better, what these rotations and what doing PCAs is. But does anybody have any questions? Oh, I guess I should probably, now that we've shown that, as far as pulling up in R, pulling up these things, if we look at PCA OB4, which from here on out we won't go back to, we won't be using the PCA, just the regular PCA that we did up here. We're completely done with that PCA. That PCA was only to look at the Kaiser's criterion, scree plots, etc., and requiring 19 components. Now that we're past that and we've decided we need 3, 4, or 5, no more of that PR comp function. So down here for our communalities, conveniently there is a thing called communality, and if you run that, it'll give you all of the communalities. I'm going to take that at another step of wrapping that in sort, just so that it sorts it by, in order from, lowest to highest. And then I'm also going to go ahead and wrap that in round, just so that I get, 3 decimal places. So now we pull out those communalities and also sort them so we can right away see Discrim 102 is our lowest and Dep 104 is our highest, and here are their values, etc.
These numbers match the output we just showed you in SPSS, and we didn't have to sort them. We could have had them in the order in which they were entered into the analysis. But for the purposes of this, we're trying to look at things like, what's the highest communality? What's the lowest communality? So what do you think that might mean for when we actually do our PCA? And Morgan and others have already previewed for us that we expect right now that depression 104 is very likely to be a marker variable, just because it has the most variance explained by extracted components. And that Discrim 102 is probably not going to be a highly loaded one, although we don't know. These are not loadings. These are just variance explained. But it does sort of suggest to us that maybe certain variables are going to be strong and other variables are going to be a little bit weaker.
All right. Any questions about communalities before we move on to the next piece? Going once. Going twice. All right, once we move on to number 9, it's asking us to look at the obtained correlation matrix of the unrotated model and the reproduced correlation matrix. So we need to we don't have an unrotated model yet. So all we're going to do here, copy and paste the PCA that we just did, change PCA OB4 to PCA none 4. And rotation, instead of oblumen, just tell it none. Everything else stays the same. So now once we run that line, we have a new PCA none 4. No rotation, 4 components, 4 factors. For our reproduced correlation matrix, there's a function called factor.model. And in that factor model, we'll tell it we want to do a factor model of the loadings from this unrotated PCA. So PCA none 4 $ loadings. And we could run this as is, but this will give us, the full reproduced correlation matrix. So to make this a little bit easier to read, we're gonna wrap that in that lower mat function that we used. and then also tell it digits equals 3. And now when we run it, we'll have just that lower matrix. So this is our reproduced correlation matrix. You're muted.
Okay, let's just hang on 1 second. Let's make sure everybody was able to run the analyses. I actually had an error, so let me see if I can figure it out. Can I see your code for lower mat again?
Right there.
Oh, I forgot a parentheses. Okay. So I know at least Linda's got it. How are others? Got it. Oh, good. You guys are so good. Awesome. Do we, are we going to be talking here in just a moment about, well, I guess that's the next question.
Yep.
It might be worthwhile to explain what it is that we're doing here. Again, sort of big picture. Okay.
Yeah, that's what I figured you could discuss what these reproduced correlation matrices are, and then we'll pull up that residual and because then like B is looking at the actual correlation.
Right. Okay. So the PCA that we just ran is one where we didn't do any rotation of any kind. Can someone remind us of why do we rotate?
Is it to figure out which components we want to keep that fit the model best for parsimony?
Yeah, the rotation doesn't help us with component extraction. It helps us with other stuff.
Help with interpretation.
Yeah, Lauren's exactly right. It's messy, and I want you to have the experience of doing this. It's messy to interpret an unrotated PCA. Just like we talked about in class, that if you have it unrotated, it's sometimes hard to tell if a particular, how a particular variable loads on one versus another component, and if it more strongly loads on, say, component 1 than 2. And so rotation allows us to sort of like, almost like with the microscope, where we can more clearly focus. So that's basically what rotation does. So I want us to have the experience of looking at an unfocused PCA, and then we're going to look at what happens when we do that rotation and we basically focus more. So stretch those loadings so that it's more clear that, you know, this variable really belongs here and this variable really belongs in this other space. The other thing that we're going to look at now is how what it means to basically explain variance in variables based on extracted components. So we're going to be comparing the original correlation matrix, which shows you the associations between the different variables. And then we're going to be, once you do an extraction, once you say take out 4 components and you've lost some information, the computer is basically saying, okay, well, with the information I have, which is less than full information, here is my best guess about the correlation between Discrim 101 and 102, or DEP 101 and Discrim 104. So it is estimating the actual correlations between variables based on less than full information. So based on here's my best guess. And what we want to know is, how good is your guess? If we do a good job with our extraction, we're not going to have a lot of correlations that are really far off the real correlations from the full 19 variables. So that's what we're looking at now. It's another way to test the quality of our PCA, is to see if we can reproduce the correlations among the original variables when we have less than full information. Back to you, Austin.
All right, and so then, so when we look at our reproduced correlation between Discrim 101 and Discrim 102, we see that reproduced correlation is 0.353. And then on B, it's asking what's the actual correlation between these two. And so we just use our regular core function and tell it what's the correlation between Discrim 101 and Discrim 102. Here I just went back to the full data frame instead of the subset. It doesn't really matter if you would have used the subset. But when we run that, we see that the actual correlation is R equals 0.173. And so then, like, what's the difference between those two values? Well, if it's 0.353 minus 0.173, the difference between those is 0.18. And so you can look at that there's a different correlation matrix that's possible, instead of having to manually look through these and say, like, all right, well, what are my correlations, and then what are the differences of all these correlations? Because, as Anna was just talking about, basically we're wanting to look at, like, how, are the correlations still looking somewhat like they should be looking after we've lost some of this information. And so there's a thing called the residual correlation matrix. So if we look at the PCA none $ residual, this is going to give us our residual correlation matrix, but again, it's one giant block. So once again, I'm going to wrap that in lower mat and tell it I want digits to equal 3. And so now we're looking at the, and you notice that here where we manually calculated the difference between the reproduced correlation and the actual correlation, we got 0.18. Here in this residual correlation matrix, we see that that's what it gives us. So in other words, when we're looking at this, at these residuals, this is the difference in the actual correlations and reproduced correlations for each of these variables.
Ideally, guys, what would we like? What are we hoping to find in the residual matrix?
Smaller the better.
Yeah, Casey says small values. We'd really love them to be zeros. Exactly, Cameron, exactly. I mean, ideally, with less than full information, we still have perfect or near perfect replicability of the associations among our variables. So what we're really, really hoping for in this residual matrix is that most of the correlations are very small. And we define very small sort of conventionally by looking at how many of them are smaller than an absolute value of 0.05. And so if we have a lot of our residuals, meaning, errors that we made in estimating correlations, the original correlations, if a lot of them are above 0.05, then it might speak to the fact that we maybe need to extract more components, or that we're not doing enough of a good job. We're losing too much information. And so the next question we're going to look at is how to figure out quickly, so that you don't have to hand count, how many of these residual correlations, meaning the errors that we made in estimating the correlation, are above 0.05.
Yeah, so here I'm going to start just by copying and pasting what we had for getting that residual matrix, because I still just want that lower triangle, round it to 3 just to make it pretty. And then as far as getting the absolute values of these, instead of just having the PCA none for residual here, We're going to wrap that in ABS, which is the absolute value function. So taking what we did on D and just wrapping the actual PCA none for residual in absolute value to get those absolute values. Now I'm going to store that as an object that I just call absmat for absolute value matrix. And so if we look at that, like, it gives us just a list of the values, but it, took the absolute values of those. And so now we want to see how many of these and what percentage of these are greater than 0.05. And so we can make that a logical test. If we just say absmat is greater than 5 or 0.05, it'll give us a bunch of trues and falses. If we sum that, then it now will tell us, like, trues equal 1, falses equal 0. So it now will tell us that we have 61 of these, the absolute values are greater than 0.05. And if we're wanting to see that as a percentage, then all we need to do is divide that by the length of absmat. And it will tell us, about 35.7% of our residual correlations have an absolute value greater than 0.05. So again, all we're doing is we're taking our residual correlations. The reason that we're on this one, you have to use the lower matrix, because if not, it's redundant. But in other words, here where we see that, like, oh, there's 61. If we didn't use the lower matrix to cut down the non-redundant things, this would tell us that we had 132 or 122 things, because each one would have 2 of the same value. So by using that lower matrix of the absolute values of the residuals to create absmat, we now have, basically, think of it as a list of the absolute values of all of the non-redundant correlations. If you turn it into a logical test and sum it, it will give you the count of 61. Divide that by the length, and you now have the percentage of 35.7%.
So we have a couple of folks who are getting some errors. So let's pause for a moment. I had also been getting errors, Josh, and I had put a parentheses in the wrong space. Where is your error?
Looks like I was missing a. Okay, that was it. It was a parentheses. Thank you.
Same thing that happened to me. Anyone else struggling to get this? Let me ask it another way. Is everyone else able to get your 61 values? Yay. Awesome. Okay. Just Josh and I who are missing the parentheses.
Yay.
Okay. Back to you, Austin.
All right. So now we'll get to our first. We may not make it completely through number 10 today, but this is where we're gonna do, for the first time, we're gonna, like, write out a CSV and do some, like, manual highlighting and sorting and trying to better understand these component matrices. So what we want to do here is we're going to write a CSV with this component matrix, which is the loadings. So PCA none for $ loadings is the actual component matrix. But when you look here, you'll see that it, by default, if you just run that loadings, it's going to suppress some stuff. And we have these blank values here, and we don't want that for what we're doing right now. So we're actually going to wrap that in a function called unclass. And again, this is just, all this is going to do is fill in all those blanks and not suppress viewing some of these. So now that we have this unclass, let's go ahead and wrap that in round as well. So let's round that to 3. And now we're going to write this out as a CSV. But right now it's not in a data frame technically and properly. So just pipe that into data frame. And then like we had earlier, where if you look at this, it looks like these are, this is a column of the names, but it's actually not. Those are the row names. But we need these values in our data set as well. So we're going to add in row names to column. And then pipe that into write_CSV. And we'll call this unrotated matrix.csv. And once you run that in your in the folder of your working directory, you should now see a CSV called whatever you decided to name it there. And so go ahead and get that pulled up.
Okay, give us a second here.
Mm-hmm.
I'm getting 1s and 0s for mine.
Is it because of a rounding issue?
Where are you getting 1s and 0s?
For the, I guess, the loadings.
If you just type in PCA none for $loadings.
Yeah.
Austin, where do I find my CSV?
In your working directory.
Okay, 1 second. Also, Jake is saying, how do you make the numbers rounded in Excel to 3 digits without auto-correcting? There's a cool little icon at the top of Excel that shows like an X and an arrow pointing to the left, or an X and an arrow pointing to the right.
Right here.
Can you make yours a little bigger? Yeah, so if you point it to the left, it increases, it increases the number of decimals, and if you point it to the right, it decreases.
Did you get yours working, Josh, or is it still?
Yeah, no, it's still.
But what was this working when we were doing the residual stuff?
Round function that it adjusts them to 1s and 0s. If that makes sense.
Josh, can you say again, what is it?
So whenever I use the round function on the unclassed PCA none loadings, it defaults them to round to 1 or 0.
Oh, right. You didn't add the 3 here.
3?
I did not.
Yeah, so that's if you just put round, then it just rounds it to, the nearest whole number.
Gotcha.
So Cameron asks, how do you get it to open not as an R script, which is what happened to me too, but actually as a CSV?
The CSV opened as an R script?
It is. In mine, it opened like it would a data frame. I'm assuming that's what Cameron did too.
Strange. I mean, if you go into your folder, at least with if you right click on it, there should be an open with thing. If you're on Macs, I know that if you, instead of clicking open with, if you click get info, and it pops up with the document info, there's an option that says open with, and you can change it to something, and then there's a button that says change all, and that'll make it to where all future CSVs automatically open in Excel. With Windows, there's something similar, but I can't remember the exact wording, but there's like you right click on it and you can click open with and like more options or something. And then once you open up that more options and click on Excel, there's somewhere in that process is a little checkbox that says like do this for all documents of this type or something like that. But I can't remember what it is there on Windows. Does that?
So I didn't have that option, but Cameron, if you are in your files, part of your R, I don't know, desktop, and you see your CSV, then if you click on more, then I think you can go to working directory or show folder in new window. And then you can open it from there because it'll show it in your.
Oh, right. I see why now. I was under the impression that you were open. I just have like my actual working directory folder opened on my other screen, which is why like when I click on it, it opens in Excel. Yeah, if you are just clicking on a CSV in R, then it just opens it up in View.
But if you go to so it looks like Cameron got it. Did everyone else get their CSV file open? Yay, great. Good. So we're going to be working outside of R for a little bit for the next couple of items, and we're going to be working in this CSV file. We're going to be doing a lot of basically coloring
And
because we're back in kindergarten.
I turned off my share screen, Anna, if you want to share yours as you're doing some coloring and such.
Sure. 1 second then. Let me. One thing that I'll need your help to tell me, let's see, share, what is each item? So what is the item on the homework assignment? Okay, can everyone see my Excel file?
Yep.
Perfect. Okay, so we've extracted 4 components. This is component 1, and then all the loadings are on there. This is component 2 with all the variable loadings, component 3 and component 4. And what we're going to start doing now is identifying in this is an unrotated matrix, where things fall. So Austin, what's the very next question on the assignment?
The next question is about complex loadings. How many have complex loadings?
Okay, so at what point did we decide something loads on a factor? What is the cutoff for deciding something loads on a factor?
What is it like 0.5 or 0.6, right?
That's true for a marker variable, but that's higher than for just saying it loads.
Okay. So is it 0.32, just greater than that cutoff?
Yes, that's exactly right. So I'm going to color principal component 1 as yellow and just highlight it as yellow. That way it helps me see. I'm going to make principal component 2 green. You can make them whatever color you want. I'm going to make the third one some orange kind of color and the fourth one a bluish color. Okay. And that's only to help us more clearly see what belongs where. So I'm going to start with principal component 1 and highlight in yellow anything that is above a 0.32 absolute value. So what is the first one that we have that actually seems to load on component 1?
E1.
This one does. So I'm going to highlight it. And actually, this one does as well. It's above 0.32. All of these do.
All the self-esteems.
Yep. But also look at this. All of these depression ones do too, right? Is that clear to everyone? Good. What about in the second principal component?
Discrim 105.
What about 101?
Oh, yep, and 101 and 102.
Actually, a bunch of the discrim ones, but also a bunch of the self-esteem, or at least a few of the self-esteem ones. And that's it. Those are the ones that go on 2. Let's look at component 3, which again, I'm highlighting in orange, but you can do whatever color you want. So the ones that are above 0.3, we have a couple of discrim.
Why is discrim 102 not above 0.3? Does that not
Oh,
count?
I'm sorry, I was doing 0.32.
0.32.
Oh,
So in this component 3, we've got a couple of the discrims and all the depression ones. And then in this fourth component, which I'm highlighting in blue, I've got one of the discrim ones, couple of self-esteem ones. That's it, right? So is everyone with me so far?
Yeah, I have a question, Anna.
Yes.
How loose is the 0.3 versus 2 distinction?
0.32 is the more common thing you're going to see, because 0.32, if you square it, is 10% of the variance that that variable shares with that component.
Right. So it's more conservative.
Correct. But whenever you present your results, you just need to be clear about how you made that decision. So we're looking right now at complex loaded items, and we're defining complex loaded as those that load 0.32 or higher on more than one component. But as long as you specify that in your article, you can do 0.3 or 0.32.
Okay.
So based on this information, these highlights, what do we know about the loadings of Discrim 101? Is it complex? Is it simple? Or an outlier?
Complex.
Complex because it loads 0.32 or higher on more than one component, right? Or what I like to call my, polygamous variables, right? How about Discrim 102?
It's simple.
Yeah, Discrim 102 is simple. Do you see any variables here that are outlier variables that don't actually load on anything?
They all seem to load, so I think no.
You're right. We don't have any outliers among the variables, but we do have quite a few, and this is why I like to highlight, because it makes it really easy to visualize. We do have quite a few that load complexly. How many complexly loaded variables do we have?
It looks like all but 2, 3, 4, 5, 6, 7. All but 7.
So 12.
Yeah.
And is that what others are seeing too? I can no longer see everyone's face, so.
11, right?
1,
minus
2,
11.
3, 4, 5, 6, 7, 8, 9, 10, 11 of them.
What are we counting again?
We're counting how many variables load 0.32 or higher on more than one component. So basically, if we've, like in Discrim 101 here, we have it highlighted as loading onto both PC2 and PC3, which makes it complex. Discrim 102, however, only loads on PC2, so it's simple. So we're counting how many complex loaded items we have.
And there are 11 complex loaded or 11 simple?
I counted 11 complex. Is that what you guys found?
Yeah, 11 complex.
Austin, what's our next question?
The next question is that don't load on any components.
Which we already answered that one.
And then the last one is the highest loadings for each component.
Okay, so in component 1, which variable loads highest? And if there's chat, I can't see it, so maybe Austin, you can monitor that for us.
So, SC101 or 110?
We have a vote for SC110.
Oh, wait. Never mind.
That's SE 106.
SC106 is 0.709, and that's the highest one on this one, right?
Yeah.
What about for the second one?
Oh man, got me.
I don't know if there's chat going on, but what do you guys think for principal component 2? What's the highest loaded variable?
Discrim 103.
Good. Okay.
If
How about the next one? Yeah.
I see a few people chiming in saying that they got to take off, and that's fine. Like, this is being recorded, and I'll get it posted here later. And this is literally the last problem that we're working on today. So if you have to take off, by all means, take off, and then just check the last couple minutes of the video.
We're basically just going to go through and highlight the highest loaded ones on each component, and we'll pick it up from here next time. So we can hop off.